Hello students, welcome to the fascinating world of carbon-13 NMR, a powerful tool in molecular structure determination. Students, we know that carbon-12 is not NMR active as it has I equals 0 while carbon-13 shows spin equals to half. Hence carbon-13 NMR provides unique insights due to the low natural abundance and small magnetic moment, making its signals much weaker than those of proton. At a given field strength, 13C resonates at a frequency approximately one-fourth that of 1 Hz, highlighting the need for specialized equipment. Students, please note that the main reason carbon-13 resonates at approximately one-quarter the frequency of a proton is due to its lower gyromagnetic ratio, which directly affects the resonance frequency in NMR spectroscopy. Due to its low natural abundance, 13C coupling is rare, but 13C does couple with hydrogen atoms, which is commonly observed in spectra. Now, let's explore how 13C couples to attached protons, a crucial aspect in interpreting NMR spectra. The number of attached protons affects the 13C resonance, with the n+1 rule applying and large coupling constants observed. Here's an example of ethyl phenylacetate, showing 13C coupled to hydrogens, illustrating the complexity of the spectrum. Next, we will discuss decoupled spectra, which simplify the interpretation of 13C NMR data. Decoupling the proton spins involves using a second RF source to continuously saturate the hydrogen nuclei, simplifying the 13C spectrum. In this method, hydrogen nuclei are saturated, leading to an average zero coupling to 13C, resulting in simpler spectra. Comparing coupled and decoupled spectra of ethyl phenylacetate shows how decoupling makes interpretation easier by reducing peak overlap. Some instruments indicate the multiplicities of peaks on decoupled spectra, providing the best of both worlds for analysis. The nuclear Overhauser enhancement is a key NMR phenomenon that arises from dipolar interactions between neighboring nuclei. It provides distance-dependent information that is invaluable for determining molecular structure, stereochemistry, and spatial relationships in both small and large molecules. NO is especially powerful in biomolecular NMR for studying the conformations and interactions of complex biomolecules. Nuclear Overhauser enhancement, NO, significantly increases the intensities of carbon resonances, especially for carbons directly attached to hydrogens. Now, let's delve into the chemical shifts of 13C atoms, which vary based on their chemical environment. Here are the approximate chemical shift ranges for different types of carbon, aiding in the identification of functional groups. This correlation chart for 13C chemical shifts helps in understanding the effects of different chemical environments on the shifts. Trends in chemical shifts show how electronegative atoms and pi bonds cause downfield shifts, with carbonyl groups having the largest shifts. Aromatic ring methyl substitution patterns can be identified by the number of distinct carbon types in the NMR spectrum. Finally, let's look at some spectra to see these principles in action. Here's the proton decoupled 13C spectrum of 1-propanol, showcasing the simplicity and clarity achieved through decoupling. Let's start with 2,2-dimethylbutane. This compound has 6 carbon atoms, but only 4 signals due to symmetry. The single methyl carbon appears at 8.8 ppm, while the 3 methyl carbons on the quaternary carbon show up at 28.9 ppm. The quaternary carbon itself, which has no hydrogens, appears as a small signal at 30.4 ppm. Lastly, the methylene carbon is seen at 36.5 ppm. Next, we have bromocyclohexane. The spectrum shows distinct signals for the carbons in the ring. The bromine atom causes a downfield shift, making the carbon it is attached to appear at a lower field. Moving on to cyclohexanol, the presence of the hydroxyl group influences the chemical shifts of the carbons in the ring. The carbon attached to the O group appears downfield compared to the others. Now, let's look at toluene. The methyl group attached to the benzene ring causes a shift in the aromatic carbon signals. The spectrum shows distinct peaks for the carbons in the ring and the methyl group. Cyclohexene's spectrum is next. The double bond in the ring causes a significant shift in the chemical environment of the carbons, resulting in distinct signals for each carbon in the ring. Cyclohexanone features a carbonyl group, which causes a downfield shift in the carbon signals. The carbonyl carbon appears at a much lower field compared to the other carbons in the ring. Here we have 1,2-dichlorobenzene. The two chlorine atoms on the benzene ring cause shifts in the aromatic carbon signals, resulting in distinct peaks for each carbon in the ring. Finally, 1,3-dichlorobenzene shows how the position of chlorine atoms on the benzene ring affects the chemical shifts of the aromatic carbons. Each carbon in the ring has a distinct signal due to the influence of the chlorine atoms. Students, I hope you've gained a solid understanding of the basics of carbon-13 NMR spectroscopy. Thank you for watching. Take care, and goodbye.